Hi guys, Dr. Diaz again, and now we're going to discuss Kirchhoff rules. Well, here's a little bit of description of the Kirchhoff rule. There are ways in which resistor can be connected so that the circuit formed cannot be reduced to a single equivalent resistor. What it means that sometimes you would have in the same circuit different sources, like different batteries, but they are not connected to the same line. They might have connecting different branches, and it makes the circuit a little bit more complicated. That's why we use here the Kirchhoff rule. Two rules called Kirchhoff rule can be used, and here we go. The first rule is the junction rule. Basically says that the sum of the current going to a junction is going to be equal to 0. If you look at a junction, that connections in which you have like 3 lines there, the currents, not all of them can be going into the junctions, and not all of them can be going out of the junction. You must have at least one going in the opposite direction. Otherwise, the sum of the current is not going to be 0. It actually, like it says there, this is a statement of conservation of charge. And here's a little bit of a description of that junction rule. Here it goes. All charges that enter a given point in a circuit must leave that point. So for example, if I1 is going into the junction, here they put in that I2 and I3 must be leaving. It could happen that I1 is going to the junction and I3 is going to the junction, but I2 has to be then leaving. Or it could happen that I1 is going in, I2 is going in, but then I3 has to be leaving. But not all 3 can be going into the junction or all 3 going out. You would need at least one going in the opposite direction, right? And well, the direction, we're going to work a little bit with that direction using another rule. But if we use this case in which we said the sum of the current is going to be equal to 0, the equation we saw a moment ago, the sum of the current in a junction is equal to 0. In this case, you would say that the one going into the junction is positive and the one leaving are negative. That's why they get this equation here. I1 as the one going positive, is the one going in, minus I2 and I3 as the one going out. Next slide here we have. This is another example of the flow going in and then these going out of the junction. Now let's look at the next rule of the Kirchhoff rule. The second rule is the loop rule. Basically it says that the sum of the potentials across the element or the branches, we're going to study this later, around in any closed circuit loop must be 0. The sum of all the potentials must be 0 in those branches. This probably doesn't make much sense, but when we do the problem, we start solving the problem, you will see it makes sense. But it's important to know this rule because we're going to use this rule too. And another statement of conservation of energy. So we go here, imagine you're routing around a loop in a circuit and do another crazy stuff here. When the charge returns to the starting point, the charge in the circuit must have the same total energy, and as it had before, as the charge moved, because of the principle of conservation. You can read here another statement. We have another statement. Let me see if we can go to the problem, because then we're going to start solving the problem in a second. And well, it tells you how the decrease and increase of energy, but most important, and you guys can read this a little bit, is this what I'm going to look is the way when we apply this Kirchhoff law, but it's the way that this thing is going to be polarized. This one. When the current goes from the resistor from this side to this side, look here, this one is polarizing negative. So that means when the current goes here, it will polarize this side positive and this side negative. That's why the different potential is negative. This is important as how we can polarize all these devices when we're trying to apply Kirchhoff law, the two rules, the loops and the junction rule. And if we go the other opposite direction, it will polarize this one's positive. Oh, sorry about that. It will polarize this one positive and this one negative, right? Let's say the arrow, once the current goes here, we'll look at the negative side. Because the current goes from positive to negative, so it will be here positive, since this will be connected to the positive side of the battery, and this will be negative. And sometimes the thing that can polarize the source could be, the circuit could be the source, which is the voltage. Let's see another one. And there's another polarization depending on the direction of the loop. We're going to use the loop as needed. The loop rule can be used as often as long as the new circle or element of new circle appears in each new equation, but you will see, well, here you can read the conceptualization. Let's keep going and read this thing by your own, guys, and read this on your own, guys. Keep reading this and finalize this thing. And here is the circle that I wanted to do. We're going to do this circle in a second. Okay, so let me stop here. But look at the circuit here. What's happening? We have 3 resistors, and look what I was saying. We have more than one battery. And look, difference. You cannot say that these are in parallel with sitting whatever. No, because there's a source, there's a battery. It's not necessarily next to this one. So the circuit is actually more complicated. We're going to solve this one in a second. It's already solved in the PowerPoint, but I'm going to use my own method, and I'm going to show you this one in a second. So take care, guys. Stay tuned.